So, good morning. Today, I'm going to start a new chapter that talks about adrenergic agonists. So, what are adrenergic receptors? Adrenergic receptors, as I explained in the chapter 5, are also called adrenoceptors. And those adrenoceptors are receptors that are stimulated by two kinds of neurotransmitters mainly. One of them is called norepinephrine, and the second one is called epinephrine. And usually, the adrenergic receptors are receptors that can be activated by adrenergic drugs. So, those receptors that are activated by norepinephrine or epinephrine are called sympathomimetics. So the sympathomimetics are the receptors that are activated by adrenergic drugs, including those that mimic the norepinephrine and the epinephrine. So this activation can happen directly. What do I mean by direct activation? This is by a direct binding to the agonist on the receptor. It will be then called direct activation by direct acting agonists. The second type of activation by the adrenergic drugs is indirect. So indirect, this is by an indirect acting agonists. I mean that the agonists come and it will activate a cascade in the signaling pathway of the norepinephrine and the epinephrine. So this signaling pathway is considered as an indirect activation. So the adrenergic receptors, as they can be activated, they can be also disactivated or blocked by other adrenergic drugs. And in this case, they will be called sympatholytics. So we distinguish them two types of adrenergic receptors, those that are called adrenergic receptors sympathomimetics, and the others that are called or that bind the adrenergic receptors by blocking them and called sympatholytics. And as you can see, of course, just as a kind remember of the adrenergic neuron, an adrenergic neuron is a neuron that secretes norepinephrine. So every neuron known to secrete and release norepinephrine is then known to be an adrenergic neuron. So where it is located, this adrenergic neuron, it is found in the central nervous system as it is found in the sympathetic nervous system. And it serves a link between the ganglia and the effector organs. So this is the link between the ganglia and the ganglia that, of course, that will be located there, the ganglia and the effector organ. And the adrenergic neuron, as I said, it releases then norepinephrine, and the norepinephrine is the primary neurotransmitters released by the adrenergic neuron. And as I said before, that adrenergic neuron may secrete not only the norepinephrine, but the epinephrine. But remember that the first neuron transmitter released by the adrenergic neuron is the norepinephrine, not the epinephrine. And the epinephrine will be obtained by a modification that happened to that norepinephrine. The adrenergic drugs now act on the same adrenergic receptors, and they are located, we can find them on either presynaptic neuron. So هيدا النيورون اللي أنا عندي إياه. So, and this is the presynaptic neuron. You can find on this presynaptic neuron a receptor that allows the norepinephrine to bind back or to circle back and bind a presynaptic receptor present on the presynaptic neuron, as it can bind also a receptor present on the postsynaptic element. Then in this case it will be an effector organ. Now, how then the neurotransmission happen at the level of adrenergic neurons. To start, now this is a scheme that shows you the neuron, which is considered as the neuron, a presynaptic neuron, and this space is named synaptic space or synaptic cleft, and this is a membrane. This membrane represents the membrane of a cell that belongs to an effector organ. So to start, the pathway involving the synthesis of the neurotransmitter, first, at the membrane of the presynaptic neuron, we will be finding a transporter. This transporter co-transport tyrosine and the sodium. So when the tyrosine and sodium are present at high concentration, then they will enter inside the presynaptic neuron by this transporter. The tyrosine then will be hydroxylated. So the first step after the entry of tyrosine and sodium is the hydroxylation of tyrosine, which is a rate limiting step. What do I mean by this? If the tyrosine is not hydroxylated, then the pathway will not continue to be formed or to happen. The second step is the hydroxylation of the tyrosine lead to what we call the DOPA. And the DOPA will be converted by another mechanism into dopamine. So this pathway happens in the cytoplasm of the presynaptic neuron. Once the dopamine is synthesized, then it will be stored inside vesicles. So the dopamine enter inside a vesicle, and then it will be converted into norepinephrine. So then the norepinephrine is formed inside the vesicle. Why inside the vesicle? Because the norepinephrine is a molecule that is less stable than the dopamine. So that's why it should be protected from being degraded inside the vesicle. And note that the vesicle containing the norepinephrine should be then transported to become close to the presynaptic membrane. The transport of the vesicle need what we call an influx of calcium. So the neurotransmitter to be released, first it requires the transport or the passage of this vesicle close to the presynaptic membrane. This passage needs an entry of a concentration of a calcium. So the influx of calcium causes the fusion of the presynaptic vesicle with the presynaptic membrane. So this fusion allows the neurotransmitters present inside the vesicle to be released into the synaptic space. Note that the transport of the vesicle can be inhibited by certain drug that is called reserpine, and the release of the neurotransmitter can be also blocked by another drug that it is called guanethidine. Now, back to the pathway, or back to the fate and the destiny of the norepinephrine once it is released into the synaptic cleft. There are 4 pathways. The first one is the binding of the norepinephrine into a postsynaptic receptor. So then the postsynaptic receptor will be then activated by the binding of the neurotransmitter, leading them to an intracellular response. The second fate is the circling back of the norepinephrine and its reuptake by a transporter present on the presynaptic membrane, allowing the re-entry of the norepinephrine into the presynaptic neuron again, where it has one of two, or the two other fates. So, or it will be then restored inside the vesicle for further release, or degraded by enzymes present in mitochondria, such as the MAO, abbreviation of monoamine oxidase. So the metabolite formed after being oxidized by the monoamine oxidase are then released by following the urinary pathway. The third fate is the metabolism of the norepinephrine by another enzyme. This time is present in the synaptic cleft, and it is called COMT, which is an abbreviation of the catechol O methyltransferase. This enzyme also converts the norepinephrine into metabolites that are inactive and that also eliminated from the body following the urinary pathway. The fate number 4 of the norepinephrine is to bind its second receptor, which is now present in the presynaptic membrane and is called a presynaptic receptor. So this binding causes further mechanisms. Now, note that the removal of the norepinephrine or its reuptake, or its removal from the cleft and its reuptake by this transporter can be inhibited by, for example, the cocaine and the imipramine. So those drugs will be discussed further in the next session. Now, the steps are detailed here. The first step is the synthesis of norepinephrine, how it is synthesized. As I said previously, the synthesis of the norepinephrine requires the entry of tyrosine, and the tyrosine is entered by a carrier or by a transporter that it is coupled to the sodium into the neuron. Once the tyrosine enters inside the neuron, it will be then hydroxylated, as I said, which is the rate-limiting step. This is an important step, the hydroxylation of tyrosine into L-DOPA by the tyrosine hydroxylase. After that, the L-DOPA will be then decarboxylated by another enzyme that is called aromatic amino acid decarboxylase into dopamine. And then the dopamine will be then formed in the presynaptic neuron. After its synthesis in the presynaptic neuron, the dopamine need to enter a vesicle. Need to enter this vesicle, as you can see in this scheme. So the dopamine will be then transported into synaptic vesicle, but this transport, as I said, is then blocked by the reserpine. So after that, the dopamine need to be hydroxylated by a dopamine hydroxylase into norepinephrine. And this step happens inside the vesicle. And now we can find inside the vesicle the norepinephrine instead of the dopamine, because the dopamine is hydroxylated into norepinephrine. The step number 3 is the removal of or the release of norepinephrine. So the norepinephrine should be released, or this release requires the transport of the vesicle close to the presynaptic membrane. So how then the vesicle is transported into the presynaptic membrane? This transport requires an arrival of an action potential that it is followed by an influx of ions, calcium. So at the nerve junction, from many sides, as you can see, the calcium enters, causing a stimulation of the vesicle to be transported. Then the vesicle transport and then fuse with the cell membrane of the presynaptic neuron, causing them a release of the neurotransmitter by a process called exocytosis into the synapse. So this step can be inhibited or blocked by a drug that is called guanidine. Now, the step number 4 is after the binding or after the releasing of the norepinephrine into the synaptic cleft that it is considered here, then one of its fate, as I said, is the binding of its receptor present on the postsynaptic element, that it is present on the cell membrane of an effector organ. This binding triggers a cascade of events involving the activation of an enzyme that it is called the adenylate or adenylyl cyclase, causing an increase of or in the concentration of a second messenger known as the cyclic adenosine monophosphate that its high concentration cause an activation of kinases involving or involved in phosphorylating other proteins present inside cell, then leading to an intracellular response. So another binding to the norepinephrine, they do not only bind the postsynaptic receptor, but they are also able to bind a presynaptic receptor. As you can see, this is a receptor present on the presynaptic element, other than the one present on the postsynaptic element. So as they have the possibility to bind the receptor present on the postsynaptic element, they have also an affinity to bind receptor present on the presynaptic receptor, causing a modulation in the release then of the neurotransmitter. Now, the step number 5 requires the removal of the norepinephrine by many ways. So this is a third fate, if you want. So the two past fates were the binding of the norepinephrine to its postsynaptic receptor. The second fate is the binding of the norepinephrine to the presynaptic receptor. Now the third fate is their diffusion out of the synapse. So it is possible that when the norepinephrine that it is released by, for example, the adrenal gland, it is possible to leave the synapse and goes to the systemic circulation, where it enters then the circulation and then goes toward any visceral organs or any other effector. The other fate is the possibility or the metabolization or metabolism of the noradrenaline or norepinephrine by the catechol O methyltransferase into metabolite ready to be eliminated in the urine. And this metabolization by the COMT happen in the synaptic space, as you can see in this scheme. The other fate is the possibility of the norepinephrine to be reuptaken back into the presynaptic neuron by a transporter called NET, which is an abbreviation of sodium chloride-dependent norepinephrine transporter. So this step is considered as the primary mechanism that terminate the effect of the norepinephrine. So once the effect of the norepinephrine is ended, then the norepinephrine has to enter back by this transporter into the presynaptic neuron. This step, of course, in certain cases, can be inhibited by other drugs, such as TCA, tricyclic antidepressants, or by serotonin-norepinephrine reuptake inhibitors. Remember that the norepinephrine belongs to the family of catecholamine as the serotonin, or it can be also inhibited by cocaine. Such, for example, the patients or the individuals who are using cocaine or who are taking frequently the cocaine comes and sits on the NET, blocking the capacity of this transporter to letting the norepinephrine reuptaken back. And finally, regarding the other potential fates of the recaptured norepinephrine, now the question is, if the norepinephrine is reuptaken by the NET transporter present here, the question is, what happened to the norepinephrine that enters inside the presynaptic neuron? There are two possibilities. The first possibility is to be taken and stored inside a synaptic vesicle by an amine transporter system present in the vesicle. And the stored norepinephrine or noradrenaline in the vesicle is needed for maybe a further release again. The second fate of the norepinephrine, other than being stored inside vesicle, is to be metabolized. And this metabolization required the presence of an enzyme called monoamine oxidase that oxidize the norepinephrine into metabolites that are later on eliminated from the body by the urinary pathway. Note that the monoamine oxidase is an enzyme present in the mitochondria, and therefore its oxidation by the monoamine oxidase happens then inside the mitochondria. Now, what are the types of adrenergic receptors?